Rosalind Franklin is a soon-to-take-off mission run jointly by the European Space Agency and Russian Roscosmos Agency, which aims to gain valuable information about Mars. This mission is a project of the ExoMars astrobiology project, run through an international collaboration. It is one of the largest worldwide projects in the fields of space exploration. The Rosalind Franklin rover will attempt a touchdown in the northern hemisphere of Mars, at a region named Oxyoplanum sometime between April and July of 2023, approximately 9 months after its initial launch date of late September or early October in 2022. Although this may seem like quite a long while away now, the processes to mission launch are being established currently. As the rover enters the Martian atmosphere, its path will be slowed by a total of 4 parachutes, which, when combined with braking rockets, will allow a smooth descent to the surface. It is of course vital that no components of the rover are damaged, so this example goes to show the extreme levels of detail and thought put into the development of an extraplanetary visit. The payload of the rover, the weight consisting of instruments and cargo, weighs just 26 kilograms, but contains everything necessary to scan the Martian terrain for morphological and chemical lifeform signatures. Morphological refers to the structure of living organisms, and chemical refers to the interaction of biological substances. Let's take a closer look at the scientific instruments we would find in our payload. Hadron RM. This is the onboard neutron spectrometer, enclosed within the body of the rover. Hydrated minerals and water held below the surface is of great interest to this experiment. Combined with wisdom, this tool allows us to search for areas of effective drilling and sampling. Close-up imager, CLAPI. This instrument has a fascinating role, studying rock samples at a very close distance of approximately 50 centimeters. CLAPI has a micrometer resolution, allowing it to study the fine structure of interesting samples. 2 mirrors and a calibration mirror allow high-resolution images to be obtained at large distances. Mars Multispectral Imager for Subsurface Studies, MA-MISS. Located inside the main drill is an infrared spectrometer. This payload component acts to further support the characterization of the local geographical layout of the planet and explore how water-related minerals are distributed. The data taken by MI-MISS and the internal spectrometers will play a crucial role in our interpretation of the original conditions from which Martian rock formed. We hope to build up an idea of how the atmosphere, climate, and crust of Mars formed, as well, of course, as for signs of past life. There are many other components, and I'd encourage you to go and read more about them if they've piqued your interest. I hope we've now illustrated the complexity of a mission like this and how it requires many components all working together in symphony. Once the rover settles upon Martian soil, discovery can begin. By digging just a few meters below the surface of the rocky planet, scientists hope to learn more about what makes Mars tick. We want to look into the possibility of finding organic, carbon-based material indicative of life. Using a technique called Raman spectroscopy, we hope to locate biomolecules and biosignatures from past life. Most organisms are composed of 4 primary elements: carbon, nitrogen, hydrogen, and oxygen, the building blocks of life, making up 96% of human body mass. The search for these will be carried out through Raman spectroscopy. Now, let's move on to the physics behind it. The main scientific subject of our conversation today is Raman spectroscopy. A big term, I know. Let's break it down. Spectroscopy is a scientific technique that allows us to measure the intensity of radiation as its wavelength changes. Wavelength refers to the physical distance between 2 points equal in phase, separated by a single cycle of a wave as it progresses through a medium or vacuum. The intensity of a wave is the power transferred per unit area by the wave. We think of this as the amount of energy moved from one place to another in a given time frame. In spectroscopy, we ask the question, how are these two things related? And how is it useful to us? Different molecules have different chemical properties, just as every snowflake is different, and all humans have different handwriting. By shining light through a sample of a material, we can see what we are measuring, through analytical techniques. Samples of Martian rock from below the surface are obtained via drilling. Spectroscopy is utilized to tell us information about the content of Mars, which allows us to build up detailed images of given regions we sample. Raman spectroscopy is a specific technique within this field, where we try to find the vibrational modes of molecules, where the motions of atoms within the molecule follow a sinusoidal path, and each point has a fixed frequency and phase relationship. Light shined through a sample leads to interaction between incident photons and the vibrational motion of the molecule. This results in excitations of the system, which allows us to determine key information, including the types of elements composing a molecule and its structure. By scanning through the terrain of Mars with a host of instruments on Rosalind Franklin, new and detailed analysis can support our current knowledge of the fourth closest planet to the Sun. The results of this mission will play a huge role in our understanding of the universe we live in, and potential new discoveries could shape space travel for decades to come. The cost of this is staggeringly in the billions, taking years of insight, detailing, planning, and international cooperation between countries and their respective space agencies to make this project go from conception to reality. Extraterrestrial discovery is archaeology of the stars, and dreams of rapid human occupation will become reality in our lifetime if predicted correctly by many leading entrepreneurs and astronomers. We could ask ourselves grandiose questions about the results of the mission, such as whether human inhabitation on Mars will start as a realization of ExoMars. We'll avoid that for now. Similar projects worldwide have Mars as their common goal. For example, the ongoing programs of NASA hope to send humans onto the surface of Mars by the 2030s, only a decade away. Meanwhile, SpaceX has ambition to see humans on Mars by 2024, merely a single year after Rosalind Franklin intends to touch down. Multiple countries have their own orbiters currently deployed, such as India, China, and the United States. Akin to the space race of the 60s and 70s, multiple competitors drive both innovation and collaboration, so it is interesting to further note what a wonderful age we are living in with regards to space exploration.